So let's determine the foot of the perpendicular using this criteria. Let's say that point P, okay, for a while, let's say point P and point Q are on the same line L. And X is not on that L, but it's actually the considered point on the perpendicular line to line L. So how do we determine this? Again, in our high school years, we usually start with the process of identifying the equation of the line L, then getting its slope, using that slope to get the slope of the perpendicular line using the negative reciprocal. Then that slope and this point, yeah, the point slope form, right? We can determine the equation of a line. And then we now have the new equation of a line of the perpendicular line to L, and together with the equation of a line of L, we can solve for the point of intersection. That is the foot of perpendicular. This time, let's illustrate that with our process, the usual process that we do when determining the foot of perpendicular using vectors. So let's start with plotting first the point P and Q. Let me plot here points P and Q on our Cartesian plane, considering that each grid is 1. So you have here -2, and then 5. 2, 3, 4, and 5. This is actually point P at -2 and 5. And then for Q is a 3, 1, 2, 3, and -2. This is our point Q. It's 3 and -2. And our X is a point not on that line, right? It's actually 2 and 5, so somewhere here. This is our X, that's 2 and 5. So basically, if you would like to draw a certain line, hopefully my line could actually hit those points immediately. I'm just hoping that it's okay with you that I have this line here. So arrowhead and arrowhead, okay? Assuming that it really intersects those 2 points P and Q, and then we have here our point X. In short, the foot of the perpendicular is somewhere here. If this will be perpendicular somewhere here. Let's verify the location later as we try to solve for F. So we're looking for F. Okay. Now, what would be the process? What would be the formula? We are given with the formula F is equal to X, your point X, minus the inner product of X minus P. Okay. Any point on that line. Then N, or the normal unit vector, and you have here the unit normal vector as well. So let's try to identify first our unit normal vectors. Okay, so we start with the vector first, vector V, then we get the normal vector, and then the unit normal vector. That's the process, right? To solve for our vectors, you can have here Q minus P. This is actually the direction vector of your line L. So your Q is a 3, -2, minus -2, and 5. So you'll have here 3 minus -2, -2 minus 5. So you have here 3 plus 2 is 5. And then you will have here -7. This is our vector V. Now, our normal vector will use the components of -v sub 2 and v sub 1. Please try to review this, okay? So our v sub 1 is this one here. This is our v sub 2. So our normal vector would be negative of -7. So it's let's have something like this because we are trying to learn the entire process. So you will have here +7 and +5. This is our normal vector, the direction vector of the normal line, which is the perpendicular line to this, which will cover X and of course F, assuming to be true, right? But this is not the value we're going to place here because it's the unit normal vector. Since take note that we are on the unit vector, or specifically on unit normal vector, let us of course try to determine first the length of the set, because if we're going to take the unit normal vector, it's actually the normal vector itself over the length of the normal vector, as indicated in one of the videos in this playlist rather, as we discuss the unit vector. So the length of your normal vector is actually the square root, okay, of the squares of your first and second components, right? I'm not going to use v sub 1 and v sub 2 because it was already used in determining the normal vector from a direction vector. So basically, it's just 7 squared plus 5 squared. For the purpose of this, you may also try to review some specific videos specifically on the determination of unit normal vector. This is actually the square root of 49 plus 25, we will get a square root of 74 for the length of our normal vector. So that's what would be substituted here. So you will have in parenthesis notation, our normal vector is 7 and 5, and you have here the square root of 74. Or in other references, our unit normal vector is indicated as 7 over square root of 74, and you have here 5 over square root of 74. Now that we have our unit normal vector, let's go back to the formula. We already have our x as identified here, and our p is still, since we are given with p, let's use p. You may also use q if you would like to, but since p is already given, let's use that. So we'll have here the foot of the perpendicular is equal to your x minus, you have the inner product of x minus p, or the vector of line passing through x and p, times your unit normal vector. With the inner product with your unit normal vector times another unit normal vector. Your x here was 2 and 5. It's here. So you have 2 and 5 minus, again, your x was 2 and 5 minus your p is negative 2 and 5. Negative 2 and 5. Your unit normal vector is 7 over square root of 74. 5 over square root of 74. Again, we don't need to rationalize it later probably. And then you will have 7 over square root of 74 and 5 over square root of 74. So here you will have 2, 5, then 2 minus negative 2 is 4, and you have 0 here. Having 0 will help us in determining the what they call this one, the inner product, because we'll be multiplying them, right? So you have here 7 over square root of 74 and 5 over square root of 74. The result of the inner product will still be multiplied by 7 over square root of 74 and 5 over square root of 74. Okay? So still you have 2 and 5. Again, our goal is to solve for this foot. So let's try to determine. Again, it's on the second quadrant, so we'll be expecting x to be negative and y to be positive. Hopefully, we can actually get that using this process, because this is really the formula intended for that. Let's continue here. So you have minus, the inner product is actually, okay, 4 times that is 28 over square root of 74 plus 0 times this. Let me use other color to represent that. Okay, so you have 0 times that is 0. Okay, so that's 0, right? That's why it's nice to use 0 or possibility of 0 times. Now again, inner product is a scalar, so it's the sum of the product, so we don't need to have square roots for that. So you have 7 over square root of 74 and then 5 over square root of 74. When we multiply, take note, it's a scalar. 2 and 5, now it becomes 28 over square root of 74 times your unit normal vector. Okay, so basically, as mentioned, the square root later on will still be simplified, because you will have 2 and 5. As you multiply that, 28 times 7, let me use a calculator here. 28 times 7, you will get 196. Sorry, this should be minus, change the color. 196 over the product of these two. Of course, the square root will no longer be there, so you have 74, and then the other one is 28 times 5. Okay, times 5, you will have 140. 140 over now positive 74. Okay, so no need to rationalize earlier, because the square roots will still be removed as we have products of the notation. So with that, simply combine this. So you will have 2 minus 196 over 74. I haven't simplified that in the meantime, but of course you can simplify that on your own. So we have 2, let's have 196 divided by 74. If you may, let's try to combine them automatically. You may, of course, use your calculators. 2 minus 196 divided by 74. But, of course, it could still be simplified, right? But let's just simply try to continue doing that. It's actually equal to negative 24 over 37 in simplest form. And you have your 5 minus, you have 140 divided by 74 or over 74. You will have a certain fraction in terms of 115 over 37. Okay, so this is actually the foot. As you can see, the x is negative, the y is positive. It somehow fits to this perspective that the point is really, or the foot is really on the second quadrant, if we're going to say that my graph here is approximately correct. And by the way, if you would like to really see the picture of that in decimal notation, that we could really look into that perspective, you have negative 24 divided by 37. It's actually rounded off more approximately 0.65. This approximation, rounding it off into decimal places. 115 divided by 37, you will actually get 3.11. Again, they are actually rounded off. So we are going to copy that here and see if our again, presumably that our graph is actually accurate. Let's try if it's on negative 0.65. So as you can see, it's here, so it's less than 1. So basically, probably it's correct. As for our what do you call this one? Our y. Alright, at this point, so probably my point is incorrect because it should be somewhere here. So if I may, I would like to redo my target. So probably it would be somewhere here for perpendicularity. For our point, which is at 2, sorry. Our point is at 2, 2, and 5. So more or less is somewhere here. So just like that. So basically, we have found the foot of the perpendicular. Again, in our high school years, we have a lot of steps. Since still here, we also have a lot of steps. But basically, since we're talking about vectors and normal vectors, so simply use those things as we solve for the foot of the perpendicular. We'll have more examples as to this. Thank you very much for watching.